February 1, 1943, 23,000 feet above Tunis, Tunisia, North Africa, Technical Sergeant Joseph Bellino stood at his flight engineer station aboard the B-17F Flying Fortress All-American, watching through the top turret glass as German Messerschmitt Bf-109 fighters tore through their bomber formation with a ferocity that suggested desperation or hatred or both, and what happened in the next 30 seconds would test every hour of technical training he'd received during his 9 months preparing for combat operations that no amount of classroom instruction could truly prepare anyone for until they experienced the reality of flying a 33-ton aircraft through hostile airspace while men tried to kill you. With bullets and cannon shells and the physics of high-altitude flight, the 97th Bombardment Group had dropped their bomb loads on the Axis-controlled port facilities at Bizerte and were turning for home when the German fighters intercepted them, and Bellino had already witnessed 2 B-17s in their formation take. Fatal damage and spiral down trailing smoke and fire, while he counted parachutes and prayed for the crews he knew personally and understood could just as easily be him falling through 20,000 feet toward either capture or death, depending on whether the parachute deployed and whether German or Italian troops would reach survivors before they bled out or froze or simply gave up. Lieutenant Kendrick Bragg, the pilot, was fighting to maintain formation position while calling out enemy fighters and coordinating defensive fire, and Bellino was tracking fuel consumption and engine temperatures and oil pressure across 4 Wright R-1820 Cyclone radial engines that each developed 1,200 horsepower when they were functioning properly, but that required constant monitoring because any of 1,000 mechanical problems could develop at any moment, especially under combat stress that pushed every component to operational limits. What Bellino didn't know, what none of the 10-man crew aboard All-American could have imagined as they fought their way through the German fighter screen, was that within 60 seconds, a crippled Bf-109 would collide with their aircraft and nearly sever the entire tail section from the fuselage, creating damage so catastrophic that witnesses in other bombers would radio base command to send rescue boats because All-American couldn't possibly survive the return flight across the Mediterranean, and that Bellino's technical knowledge and improvised repair skills would become the critical factor in whether the crew survived or joined the thousands of American airmen who'd already died in the strategic bombing campaign against Axis forces in North Africa and Europe. The next 3 hours would demonstrate both the extraordinary durability of B-17 design and the even more extraordinary ingenuity of trained flight engineers who understood their aircraft so thoroughly they could assess damage and implement repairs under conditions that would have seemed impossible to peacetime mechanics working in properly equipped hangars with full tool sets and technical manuals, proving that the American emphasis on technical training and mechanical aptitude had created a generation of airmen who could literally hold their aircraft together with improvised solutions when standard procedures had become irrelevant because the damage exceeded anything the training manuals had contemplated. The story of how American bomber crews developed the capability to repair catastrophic battle damage in mid-flight begins 2 years earlier, in 1941, when the Army Air Corps was rapidly expanding from a small peacetime force into the massive strategic bombing armada that military planners believed would be essential for defeating Germany and Japan through destruction of industrial capacity and transportation infrastructure that modern warfare required. The B-17 Flying Fortress had entered service in small numbers before Pearl Harbor, and early operational experience had revealed that while the aircraft was remarkably durable and could absorb punishment that would destroy less robust designs, its complexity meant that battle damage or mechanical failures frequently created situations where bombers had to abort missions and return to base or risk catastrophic system failures that could kill the crew. The challenge facing Training Command was how to prepare flight engineers for the impossible variety of damage scenarios they might encounter in combat when peacetime training couldn't replicate. The chaos of flying through fighter attacks and anti-aircraft fire that could damage any system on the aircraft in ways that textbooks and technical manuals couldn't predict or prescribe solutions for. The solution that emerged from training bases across the United States was emphasis on understanding aircraft systems at fundamental level rather than memorizing specific repair procedures, teaching engineers not just what to do when a particular component failed, but why that component existed and how it interacted with other systems, so they could improvise solutions when standard procedures weren't applicable. Technical Sergeant Ernest Wallace, who'd been a civilian aircraft mechanic before the war and who became one of the most respected flight engineer instructors at Lowry Field in Colorado, described the training philosophy as teaching mechanics to think like engineers, rather than teaching engineers to follow checklists. Because in combat, the checklists became useless when the damage exceeded anything the checklists anticipated, and survival required understanding principles well enough to invent solutions on the spot, using whatever materials and tools were available aboard the aircraft. The training was intensive and comprehensive, starting with months of ground school covering every system on the B-17, from engines and fuel systems, to hydraulics and electrical systems, to structural components and control surfaces, then progressing to hands-on maintenance work, where trainees learned to diagnose problems and perform repairs under supervision, and finally advancing to flight training, where engineers learned to monitor systems during actual flight operations and to recognize the subtle indicators that might precede catastrophic failures if not addressed immediately. The flight engineer's position on a B-17 was both critical and extraordinarily demanding because, unlike the pilot and co-pilot, who focused primarily on flying the aircraft, or the bombardier and navigator, who had specialized tactical roles, the engineer was responsible for monitoring every mechanical and electrical system simultaneously, while also serving as top turret gunner when enemy fighters attacked, creating workload that required constant vigilance and decision-making under conditions where mistakes could kill everyone aboard. The engineer's station was located just behind the pilot's, facing a panel with dozens of gauges and switches that displayed information about engine performance, fuel jaunty, hydraulic pressure, electrical generation, oxygen supply, and countless other parameters that had to be maintained within acceptable ranges, or the aircraft couldn't complete its mission and might not survive the return flight. During normal operations, the engineer would scan these instruments constantly, making minor adjustments to maintain optimal performance, monitoring fuel consumption, and transferring fuel between tanks to maintain proper weight distribution, managing turbocharger settings to maximize power output at high altitude, where the air was too thin for engines to develop full power without mechanical assistance, coordinating with the radio operator to ensure electrical systems were functioning properly and that battery reserves were adequate for emergency situations. When battle damage occurred or mechanical failures developed, the engineer had to diagnose the problem instantly from instrument indications or crew reports, or sometimes just from the sounds and vibrations that experienced mechanics could interpret even when instruments showed nothing abnormal, then had to decide whether the problem could be safely ignored until landing, or whether immediate repair was necessary to prevent catastrophic failure that could destroy the aircraft. The repair tools and spare parts available to flight engineers were limited by weight and space constraints because a B-17 already carried 5 tons of bombs plus fuel and ammunition and equipment and crew. So every pound of repair equipment reduced the bomb load or fuel capacity or both, which meant engineers had to be creative about using materials aboard the aircraft for purposes they weren't intended for. The standard flight engineer's toolkit included basic hand tools like wrenches and screwdrivers and pliers, some electrical wire and tape, hydraulic fluid and engine oil, spare fuses and light bulbs, oxygen system components that failed frequently in the extreme cold of high-altitude flight, and various small parts that experience showed were most likely to fail in combat. What separated effective flight engineers from merely adequate ones was the ability to assess damage quickly and accurately, to prioritize repairs based on what was critical for survival versus what could wait until landing, and to improvise solutions using materials never intended for repair work, but that could serve the purpose if properly adapted. The technical systems that flight engineers had to master represented the cutting edge of 1940s aviation technology and reflected the evolution of bomber design from relatively simple aircraft that could be maintained by mechanics, with minimal training, to complex machines that required sophisticated understanding of thermodynamics and fluid mechanics and electrical engineering and structural analysis. The four Wright R1820 Cyclone engines that powered most B-17 variants were masterpieces of mechanical engineering. Each engine consisting of 9 cylinders arranged in a radial configuration around a central crankshaft, each cylinder containing a piston that converted burning fuel into mechanical rotation through a carefully orchestrated sequence of intake and compression and ignition and exhaust that occurred hundreds of times per minute, and that generated temperatures and pressures that would destroy the engine in seconds if lubrication or cooling failed. The engines were equipped with 2-stage superchargers that compressed incoming air before it entered the cylinders, allowing the engines to maintain power at altitudes above 25,000 feet, where atmospheric pressure was less than half sea level pressure. But the superchargers added complexity and created additional failure points that engineers had to monitor continuously, because supercharger failures at altitude could cause immediate engine shutdown that might doom the aircraft if other engines were also damaged, or if the bomber was too deep in enemy territory to reach friendly lines on reduced power. The fuel system was equally complex, with multiple fuel tanks distributed throughout the wings and fuselage to provide proper weight distribution and to ensure that battle damage to one tank wouldn't immediately doom the aircraft, and with fuel transfer pumps and crossfeed valves that allowed engineers to draw fuel from any tank to any engine, or to jettison fuel if necessary to reduce weight for emergency landings. The hydraulic system powered the landing gear and flaps and turrets and bomb bay doors, operating at pressures approaching 1,500 pounds per square inch through lines that, if ruptured, would spray flammable hydraulic fluid throughout the aircraft and deprive the crew of critical systems needed for landing, which meant hydraulic leaks had to be identified and isolated quickly before they became catastrophic. The electrical system generated power from generators driven by each engine and distributed it to radios and instruments and lighting and heating systems through wiring harnesses that were vulnerable to battle damage and that, if shorted, could cause electrical fires that were among the most dangerous emergencies a bomber crew could face, because fire in flight usually meant either immediate evacuation or staying aboard to fight the fire, knowing that the aircraft might explode at any moment. When All-American took the collision that nearly severed her tail section on that February morning over Tunisia, Technical Sergeant Bellino faced damage assessment and repair challenge that exceeded anything his training had prepared him for, because the damage was so extensive that standard repair procedures were meaningless, and survival required inventing solutions that no training manual would have considered remotely feasible. The Bf-109 that collided with them had been hit by defensive fire and was either out of control or piloted by a dead or incapacitated pilot, and it struck the B-17 at an angle that drove the fighter's wing through the top of the fuselage just forward of the tail section, creating a diagonal gash 16 feet long and 4 feet wide at its widest point that essentially cut through almost everything holding the tail to the aircraft except for a few structural members along the right side and the bottom of the fuselage. The damage was visible from the flight deck when Bellino looked aft and saw daylight through the fuselage, where solid aluminum should have been, saw the tail section moving independently of the main fuselage and rotating slightly with each control input from the pilots, who were discovering that normal flight controls no longer worked the way they were supposed to, because the control cables running from the cockpit back to the elevators and rudder had been severed by the collision. The immediate assessment was that the aircraft was doomed and that the crew should prepare to bail out before structural failure caused the tail to separate completely and sent the aircraft into an uncontrollable spin. But Lieutenant Bragg decided to try maintaining level flight, while Bellino and the waist gunners assessed whether any repair was possible that might get them home. What Bellino found when he crawled aft through the radio compartment and into the damaged section was a situation that seemed hopeless. The fuselage was cut almost completely through. The tail section was held on primarily by some skin and structure along the right side and bottom. The control cables were severed, and the tail was visibly moving relative to the rest of the aircraft in ways that suggested the remaining structure couldn't possibly survive the stress of several more hours of flight. The tail gunner was trapped in his position because the floor of the fuselage no longer connected to the tail section, and there was no way for him to climb back to the main aircraft without falling through the gap. And the waist gunners reported that German fighters were still in the area and might attack again if All-American fell out of formation, which meant whatever repair Bellino attempted would have to be done while under potential fire and while the aircraft maintained formation speed and altitude. The solution Bellino improvised drew on his understanding of structural mechanics and his recognition that the primary problem wasn't the gash in the fuselage skin, but the loss of structural continuity that allowed the tail section to move independently, and that if he could somehow connect the two sections with temporary reinforcement that resisted the bending and twisting forces, then the remaining original structure might be able to carry the loads until they reached base. Bellino's repair solution involved using the parachute harness, straps and control cables from damaged systems to create improvised structural reinforcement that could tie the tail section back to the main fuselage, and the process of implementing this solution while crouched in a key section of aircraft that was moving independently from where he was standing and while wearing bulky flight gear at 23,000 feet, where the temperature was 40 degrees below zero, and where oxygen deprivation would kill him in minutes if his mask came loose, illustrates both the extraordinary physical courage and the technical ingenuity that characterized the best flight engineers. The first challenge was finding materials aboard the aircraft that could serve as structural reinforcement, because the standard toolkit contained nothing designed for major structural repair, and Bellino realized that the strongest available materials were the steel cables that had been severed when the Bf-109 struck them, cables that were each rated to handle hundreds of pounds of tension, and that, if properly routed, could effectively tie the tail section to the main fuselage by creating artificial connections that paralleled the damaged structure. The second challenge was anchoring these cables in ways that would distribute loads across still intact structural members, rather than concentrating stress at single points where the improvised attachments would tear out under flight loads, and this required understanding which parts of the damaged structure still had adequate strength to serve as attachment points, and which parts were so compromised they would fail if loaded. Bellino worked with Staff Sergeant Harry Toftoy, the right waist gunner, to route cables through the gash and around structural members that visual inspection suggested were still sound, creating a web of reinforcement that connected the tail section back to the forward fuselage through multiple load paths, so that if one attachment failed, the others could carry the load temporarily. They used parachute harness straps to create additional reinforcement for the lower section of the fuselage, where the skin was torn, but some structural members remained intact, wrapping the straps around stringers and longerons and cinching them as tight as possible to create compression that would resist the bending moments trying to separate the tail from the aircraft. The physical difficulty of this work cannot be overstated, because Bellino and Toftoy were essentially performing heavy construction labor while standing on surfaces that were vibrating and moving unpredictably, while wearing leather gloves that provided minimal dexterity in the extreme cold, while breathing through oxygen masks that restricted vision and made verbal communication nearly impossible. So they had to coordinate through hand signals and intuition developed from working together during their crew training. Every cable they routed had to be threaded through or around structural members that were irregularly spaced and often partially damaged, requiring them to bend and twist heavy steel cables using nothing but hand strength and leverage from whatever tools they could improvise, because proper cable bending equipment wasn't part of the flight engineer's kit. The parachute harness straps were easier to work with because they were fabric webbing with metal buckles, but getting them positioned properly required reaching into spaces where the fuselage skin had been peeled back and where sharp edges of torn aluminum could slice through flight suits and gloves and skin if they weren't extremely careful. The entire improvised repair took nearly 2 hours, during which the aircraft maintained formation with the rest of the bomber group, and during which German fighters made several additional passes but didn't press attacks on All-American because the visible damage made it obvious the bomber was doomed, and the German pilots apparently believed their ammunition was better spent on aircraft That might make it home if not shot down. By the time Bellino finished his repairs and crawled back to the flight engineer station, his hands were so numb from cold that he couldn't feel his fingers and his oxygen bottle was nearly exhausted from the extended time working in the damaged section where moving around and physical exertion consumed oxygen faster than sitting still at a duty station. But the tail section was noticeably more stable, and Lieutenant Bragg reported that flight controls were responding better, even though normal control authority was still severely compromised. Bellino's first priority once back at his station was checking engine parameters, because he'd been unable to monitor instruments during the 2 hours he'd spent in the damaged section, and he discovered that oil pressure on number 3 engine had been gradually declining, which suggested possible oil leak that could lead to engine seizure if not addressed, requiring him to immediately shift attention from the structural damage to a new mechanical problem that represented different type of threat to the aircraft's survival. The flight back to their base at Biskra, Algeria, covered over 400 miles, mostly over Mediterranean waters where ditching would have been necessary if the repairs failed and where survival in February water temperatures would have been measured in minutes, not hours, even if the crew successfully evacuated the aircraft before it sank. And the journey tested not just Bellino's repairs, but also the fundamental airworthiness of a B-17 that had been cut nearly in half, but that continued flying because its design incorporated redundancy and structural strength that gave it tolerance for damage that would have destroyed aircraft. Built with smaller safety margins, Lieutenant Bragg had to develop entirely new flying technique for the damaged bomber because normal control inputs produced abnormal responses, and he discovered through experimentation that he could maintain approximately level flight by using asymmetric power settings on the engines to create turning moments that compensated for the reduced rudder authority, and by making very gentle control inputs because abrupt movements caused the tail section to oscillate in ways that suggested the improvised repairs were being stressed near their limits. The navigator, Second Lieutenant Samuel Bartek, calculated a course that kept them as close to the African coast as possible, while still avoiding areas where German fighters operated from Tunisian bases, accepting longer flight time in exchange for reducing the distance they'd have to fly over open water if the aircraft broke up and ditching became necessary. The crew prepared for ditching by moving to positions that gave them best chance of evacuation if the aircraft hit water, and by ensuring that life rafts and emergency equipment were readily accessible. But they also prepared to fight to keep the aircraft flying as long as possible, because everyone understood that ditching in the Mediterranean in February meant death for anyone who didn't immediately get into a raft, and even then, survival would depend on rescue arriving within hours rather than days. Technical Sergeant Bellino monitored his instruments with intensity that bordered on obsession, because any engine problem or fuel shortage or hydraulic failure would complicate an already desperate situation, and he made continuous minor adjustments to fuel mixture and turbocharger settings to squeeze maximum efficiency from the engines that were now working harder than normal to maintain altitude with the increased drag from the damaged fuselage. The oil pressure issue on number 3 engine worsened gradually during the first hour of the return flight, and Bellino faced decision about whether to shut down the engine preemptively to prevent catastrophic failure, or to keep it running and risk having it seize at critical moment when they might need all available power. And he chose to reduce power on that engine to minimize stress while keeping it running, because shutting down would mean they'd have to descend to lower altitude, where they could maintain level flight on 3 engines and where they'd be more vulnerable to any German fighters that might intercept them. The other crew members maintained watch for German fighters and scanned the Mediterranean below for signs of rescue vessels or patrol boats that might assist if ditching became necessary. And everyone monitored the tail section through whatever vantage points they could access to watch for signs that the improvised repairs were failing or that the remaining structure was developing new cracks that would lead to catastrophic separation. Staff Sergeant Tuftoy reported approximately 90 minutes into the return flight that he could see one of the cable attachments working loose, where vibration and aerodynamic loads were gradually pulling it free from the structural member where he'd secured it. and he asked permission to go back into the damaged section to try tightening or reinforcing the attachment. But Bellino advised against it, because by that point, they were low enough on oxygen that another extended repair session would exhaust their remaining supply, and because disturbing the improvised repairs might cause more problems than it solved if the repositioning process put stress on attachments that were currently holding. The decision to leave the failing attachment alone rather than attempting to fix it represented the kind of judgment that separated experienced flight engineers from novices, the recognition that sometimes the best course of action was accepting partial degradation, rather than risking catastrophic failure by intervening when intervention might make things worse. And this judgment proved correct when the attachment did fail about 30 minutes later, but the remaining cable reinforcements held and the tail section remained attached, albeit with increased oscillation that made flying even more difficult for Lieutenant Bragg. After 3 hours and 40 minutes of flight that felt infinitely longer, All American approached Biskra, and the crew faced the final challenge of landing an aircraft whose structural integrity was questionable and whose control responses were unpredictable. And Lieutenant Bragg made the decision to attempt landing, despite the risks, because the alternative of ordering his crew to bail out over friendly territory seemed cowardly when the aircraft had survived this long and might survive a few more minutes if fortune continued favoring them. The landing approach required coordination between Bragg flying the aircraft and Bellino managing engine power settings more precisely than normal, because Bragg was using differential thrust to supplement his limited rudder authority, and the co-pilot Second Lieutenant Robert Fuller was managing flaps and landing gear manually because the hydraulic system had lost so much fluid from damaged lines that normal operation of these systems was impossible. And the entire crew understood that touchdown would subject the improvised repairs to stress that might exceed their capacity and cause catastrophic structural failure that would kill everyone aboard if the tail separated and the aircraft cartwheeled across the runway. Bragg made his approach at slightly higher speed than normal, because the damaged aircraft's handling characteristics made slow flight dangerous, and because higher speed gave him more control authority from the aerodynamic surfaces that were still functioning. But this meant touchdown would be harder and would generate higher loads on both the landing gear and the compromised fuselage structure. The base commander had ordered all emergency equipment positioned along the runway and had cleared all non-essential personnel from the area, because everyone who'd monitored the radio traffic during All Americans' return flight understood they were watching attempted landing that might end in disaster, and ground crews stood ready with firefighting equipment, and medical personnel stood ready with ambulances, though everyone recognized that if the aircraft broke up on landing there probably wouldn't be survivors to rescue. Bragg's approach was steady despite the unpredictable handling. He maintained precise control of altitude and airspeed, despite having to fight constant tendency of the aircraft to yaw and pitch in ways that normal B-17s didn't. And when he crossed the runway threshold and began his flare to touch down, every man aboard and every observer on the ground held their breath waiting to see whether the structure would hold or fail. The main landing gear touched down first, and for a moment the aircraft seemed stable. But then the tailwheel contacted the runway, and the impact transmitted shock loads through the damaged fuselage that caused visible flexing where the tail section was attached by improvised repairs. And for several seconds it appeared the tail might separate completely. But Bellino's cable reinforcements held, and the structural members that had survived the original collision held, and the aircraft rolled out along the runway, gradually decelerating until Bragg could apply brakes without fear that differential braking would cause directional control problems that might result in ground loop. When All American finally came to complete stop at the far end of the runway, Lieutenant Bragg shut down the engines, and for several seconds nobody moved because they were processing the reality that they'd survived what should have been fatal damage. And then ground crews were swarming the aircraft, expecting to find a crew that had miraculously survived unsurvivable damage, and finding instead 10 exhausted men who climbed out of the bomber moving slowly and carefully, because they'd been at high altitude for more than 7 hours and were physically and emotionally drained from the sustained stress of knowing their aircraft might disintegrate at any moment. The photographs taken of All-American after landing show damage so extensive that engineers examining them decades later express amazement that the aircraft remained controllable at all. And the images became iconic examples used in training programs to illustrate both proper damage assessment and improvised repair techniques that could save lives when standard procedures were inadequate. The most striking photograph shows the gash running diagonally through the fuselage with the tail section visibly offset from the main fuselage centerline, with Bellino's improvised cable reinforcements clearly visible holding the two sections together, and with the parachute harness straps wrapped around lower structural members providing additional support that structural engineers analyzing the photos calculated was probably carrying 20 to 30% of the total load that would have caused immediate failure if the cables had been attempting to carry everything alone. Technical Sergeant Bellino was awarded the Distinguished Flying Cross for his actions during the mission, but the citation mentioned only that he had performed emergency repairs under combat conditions, without specifying details, and Bellino himself rarely discussed the incident in detail because, like many combat veterans, he considered that he'd simply done what needed to be done and that the real heroes were the men who hadn't survived similar situations despite their best efforts. The All-American incident became legendary within the bomb groups operating from North Africa, and the story spread through the 8th Air Force in England, where strategic bombing operations against Germany were encountering damage rates that exceeded anything experienced in the Mediterranean theater, and where flight engineers were discovering that the repair techniques they'd learned in training often had to be adapted or completely reinvented to address combat damage that peacetime planning hadn't anticipated. The incident also validated the training philosophy that emphasized understanding principles over memorizing procedures, because Bellino's solution wasn't something any manual would have prescribed, but rather represented creative application of structural mechanics and materials science to a unique problem that required inventing a solution from scratch, using inadequate materials under impossible conditions. Flight engineer training programs incorporated the All-American incident as case study within months of the mission, using it to illustrate both specific techniques, like using control cables for structural reinforcement, and broader principles like the importance of distributing loads across multiple attachment points and the necessity of considering how repairs would perform under dynamic loads during flight rather than just under static loads. The training modifications that resulted from analyzing this incident and dozens of similar cases where flight engineers had improvised successful repairs under combat conditions produced measurably better outcomes in subsequent operations, with statistics showing that bombers flown by crews trained after these program revisions had higher rates of successful return from missions involving battle damage compared to crews trained before the revisions, suggesting that institutional learning was occurring and that hard-won lessons were being captured and transmitted to new crews rather than being lost when experienced personnel rotated home or were killed in action. Lieutenant Kendrick Bragg also survived the war, continued Air Force career through the Korean War, where he flew B-29 missions, retired as lieutenant colonel in 1959, and in interviews conducted during the 1970s by aviation historians, researching B-17 operations, he consistently credited Bellino's repairs as the critical factor in All-American's survival, stating that pilot skill could compensate for damaged controls but couldn't overcome structural failure, and that without the improvised reinforcement, the tail section would have separated during the flight back to base and everyone aboard would have died. And he expressed frustration that the official citation for Bellino's award didn't adequately describe what had actually been accomplished because the classification system and the bureaucratic preference for generic language meant that many acts of extraordinary courage and ingenuity during World War II were documented in ways that future generations couldn't fully appreciate or understand.